Hello, I'm going to talk on mutually orthogonal Latin square, in short MOLS. This is a novice attempt from my side to solve an open problem to find three mutually orthogonal Latin square of order 10 and about my failure. There is now no harm in admitting it. So to start with, what is the Latin square? Say Latin square of order 3. Since it is order 3, I have used three symbols 0, 1, 2, and the specialty is, say 2 is here, and in this column or in this row there will be no other position at which 2 will appear, and this is true for all the entries. So 0 is here, so in this column and in this row 0 will not be here. For any column and any row the digit appears only once. So this is the Latin square of order 3. Now this is the previous Latin square we saw, Latin square of order 3, and below it is another Latin square of order 3, a different one, just interchanging the two rows. So both are Latin square. If you check, any digit that comes in a certain position comes only once in that column or row. But on top of that, these two are mutually orthogonal, because if you superimpose two of them, so we get these values. If I superimpose the first Latin square with the second Latin square, the first box it would be 0 0, because it is 0 here, 0 here. So first box is 0 0, then it is 1 here, 1 here, so the next box is 1 1, then 2 2, then it is 1 here and 2 here, so the number 1 2 appears here. So if I take the superimposition of these two Latin square, all the 9 pairs will appear, and of course they will appear only once. So we get when one superimpose these two Latin squares, each number 0 0 0 1 0 2 1 0 1 1 1 2 2 0 2 1 and 2 2 appears once and only once. So then we call the two Latin squares to be mutually orthogonal. Now these are Latin squares of order 4. They all have the property that whenever say 3 appeared in this position, 2 3 position, and in this row or in this column it won't appear anymore. And this is true for all the three arrangements. So all of them are Latin squares of order 4, and they are mutually orthogonal. If you take the superimposition, you will get all the 16 pairs. More than that, this is called a complete set, because you cannot add any other Latin square of order 4 so that it is orthogonal to all of them. 3 is the maximum. There is a short proof of that. If you look at the position, we always start with 0 1 2 3 as the first row. That can be taken as the standard so that we can avoid replications for interchanging the symbols or permutation of rows and columns. So we can start first row with 0 1 2 3, and the 2 1 position 0 cannot come, so 1 has come here. So the choice of the digit in the second Latin square has to be 2, and the choice for the 2 1 position for the third Latin square has to be 3, because I cannot put 1 here because 1 1 has already come, so it has to be different from 1, and I had to put 3 here because it has to be different from 2, otherwise 2 2 has already appeared. So for a Latin square of order n, there can be at most n minus 1 mutually orthogonal Latin square. It is a good brain teaser to construct mutually orthogonal Latin square of order 4 by pure logic manually. It's a good brain teaser to construct the three mutually orthogonal Latin square of order 4 manually using pen and paper, and this is called the complete set. Now let us talk about Euler Spoilers, on which I already have a video. it goes as famous mathematician Euler observed that moles of order 2 and 6 do not exist. He tried to construct moles of order 10 and failed, and conjectured that moles of order 4n plus 2 do not exist. 2, 6, 10 are all of the form 4n plus 2. So he thought the 4n plus 2, he won't be nobody would be able to create mutually orthogonal Latin square. Later the conjecture was disproved, and I have a document here on it. Okay, one can go through this document, and there is also a video which is the narration of this document done by me, and it is present in the YouTube. Now there remains an unsettled question. This is an example of two mutually orthogonal Latin square of order 10. Here I give you the superimposition. You can check that, one can check that all the digits starting from 1, where is 1? Here is 2. So starting from 0, 1 to all the way to 99. 90 is here. Where is 99? 99 is here. All the pairs from 1 to 99 has appeared here, and it has been proved by complete search that a complete set, that is a set of 9 mutually orthogonal of order 10, does not exist. However, this is an open problem to find, say, 3 moles of order 10. Embedded is a master's thesis on it. So I have got a master's thesis from internet which talks on the problem of finding 3 moles of order 10. He has tried to use some mathematics, but what I did is an obvious attempt which goes like this. I created an R code. Is this opening? Yeah, let me try to show it. Here is the R code, some 200 lines code, by which I tried to construct 3 Latin square of order 4, 5, etc. So my program, when run in laptop, gives 3 moles of order 4 in 0.21 second and 3 moles of order 5 in 7.81 second. But it ran for hours. In fact, it ran over an entire weekend in the server, but failed to produce output for n equal to 7. Maybe there is a bug, I am not sure. It is going on into a loop. That may be a possibility, but otherwise I couldn't solve for n equal to 7 even. So I gave up the idea of finding 3 moles of order 10. I mean, it may require, say, 1000 hours, computer hours, which is beyond our reach, beyond my reach. So next I present an Excel macro which works fine for the case n equal to 5, 4 and 5, but runs outperform for the case n equal to 7. And I'll have a demonstration how it goes about finding, trying to find moles of order 10, 3 of them. So next is an XIV paper which people are working on this problem, and that's the end. So what remains is to show the macro. So first let us start with moles of order 4. So I have options for 4, 5. For 6 we know that the moles do not exist. So 7, 8, 9, 10. So let me start with 4. And this is the number of iterations. It would stop after a multiple of it. So let us start with 10 iterations at a time. And the number of seconds will be counted here. So I do a reset. Do you really want to reset? I said yes. So it starts with the standard format 0, 1, 2, 3, 1 here, 2 here, and 3 here. So I'd give run, and it has come up with some numbers. 10 steps are completed. Continue. You may not continue. You may say no here. Would you try solving it? No here. Then you can save the file, and again start running from there. The option is there. So if I run from here, oops, it's causing problem. So here a complete set of moles of order 4. This is the Latin square 1, this is the Latin square 2, and this is the Latin square 3. And here is the Latin superimposition of Latin square 1 and 2. Here is superimposition of Latin squares 1 and 3, and here is superimposition of Latin square 2 and 3. The formulas came from the macro so that it creates the superimpositions. So now let us try for 5. I'll do a reset. It took 3 seconds to find the three mutual orthogonal Latin square of order 4. Continue, yes. Every 10 steps it will ask me whether I want to stop or not. 30 steps, 40 steps, 50 steps, 60 steps, 70 steps, and the Latin square is complete. It took 21 seconds, and it gave me 3 Latin square 1, 2, 3 of order 5, and here are the superimpositions of them, and this is checked programmatically that it's a valid example of 3 mutual orthogonal Latin square of order 5. So next I try to run for 10 because 7 won't stop, and I give 100 as the number of loops. 100. Let me give 50. Do a reset. So it starts with the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the first entry is 1 here, 2 here, and 3 here, and these are the superimpositions. Okay, and here are all the pairs. First I'll try while running it. I'll discuss. So let me start. So it is trying to put, so it has put the pair 9 9 in the first and second Latin square, and 9 9 is already there. 9 is here, 9 is here, and 9 is here. So 9 9 9 is already there. Then it put the 9 8 pair, which is 9 here and 8 here, and found 7 to be suitable here. Then it puts 9 7. Now currently it is trying to put 8 0, and it has found 2 in the third Latin square. So it is trying to put all the pairs in the first two Latin square, following all the rules, and together, and when it succeeds to prove to put a pair in the first two Latin square, it finds another possibility for any number for the third Latin square. So this is the process. So it is currently running now for 57 seconds, almost 1 minute it is running. Now if it fails to put 1, it goes back. It backtracks up to the top. It can change, but it will take a long time, maybe, I don't know. I think I have to stop here. So it says 57 continue. I would not continue. Now it tries to give you an option to solving it by exact choice.